All right, so we'll continue on today talking about Bayesian statistics, our favorite topic that we have not yet learned about, but we're excited about because we've heard so much about Bayesian stuff. Not quite sure what it means. Okay. Well, how are you guys doing? It's fifth week. It's the end of fifth week. We're like exactly halfway through the quarter now. What's that?
Above average.
Above average. Hey, that's great. Okay. And for a lot of you, this is like your second to last quarter, right? Next quarter will be your last one ever. And then the rest of your life. And, So anyway, I hope you guys enjoy this time. Okay. All right, I forgot what I was saying. All right, we're talking about Bayesian statistics. Okay, yes. My thoughts have returned to me. We said we're going to express, rather than come to a single point estimate value of our parameter theta. So if we're talking about flipping a coin, a lot of times we would just say, what's the probability, and the textbook uses R for whatever reason, what's the probability R that the coin lands heads, okay? And then when we did maximum likelihood estimation, we came up with a single point value estimate of R, and then we would use that. With Bayesian statistics, we are not going to say we have one single value for R. Instead, we will say we're going to express our beliefs about R, and that's going to be expressed with a probability distribution. Okay, so basically, we do not get, so Bayesian statistics, we will not have I shouldn't say have, but we will not use single point estimates of our we will not use single point estimates of our statistics. Instead, we will express our beliefs about, point estimates of our, not statistics, parameters. Sorry, wrong word. Point estimates of our parameters. Instead, we will express our beliefs about the parameter with a distribution. Okay. And you'll often see in Bayesian statistics, probabilities are referred to or talked about as, kind of beliefs. What do we believe about the value of R and things like that. And if we think about a probability distribution, it does kind of make sense to talk about these things as beliefs, okay? And and so the whole reason why this is called Bayesian statistics, what is wrong? Is that we use Bayes' rule to update our beliefs. Okay, that's the reason why we call it Bayesian statistics. Okay, so the Bayesian gets its name from Bayes' rule. Right? And do you guys know who Bayes is? He was like this. He was like a monk or a pastor or a priest or something. And I don't know, he was thinking about something. All right, but anyway, what is Bayes' rule? I should learn my history a little bit better. Okay, so Bayes' rule says that the probability of B given A is equal to what? The probability of, this is conditional probability, A and B divided by the probability of A And we can split up the probability of A and B into the probability of B times the probability of A given B divided by the probability of A. Okay, right, because we learned that probability of A and B is the probability of A times the probability of B given A, but it's also equal to the probability of B times the probability of A given B. Okay, and so if we're trying to get this thing, we can split it up this way. Right? And then you probably learned about the rule of like total probabilities, right? So probability of A can be split up into the probability of A and B plus the probability of A and not B and stuff like that. And then A and B get split up like this, and A and not B gets split up the other way, right? So, you know, we're just going to be playing around with all of these things. Okay, and so with Bayes' rule, basically what we want to do is we want to learn about theta based on our data x. Okay, so we're going to have the probability of theta given our data x. This becomes, using Bayes' rule, it's the probability of theta, and here, I'm gonna just swap the position of this thing, okay? It's gonna be the probability of x given theta times the probability of theta divided by the probability of x, all right? Is this okay? This is just, all I've done is replace b and a with theta and x. And this is what we have. All right. Everything's so far so good, right? Great. I got a thumbs up. I like getting a thumbs up. All right. X given theta times, what did I say? Probability of theta divided by the probability of x. Okay. Okay, so this thing is called our posterior distribution. Basically, post means like after, and so it's the P and PM is, well, anyway, all right. This is our beliefs about theta after seeing x, okay? So let's use this. Okay, and over here, I've got probability of theta. This is called our prior distribution. This is our beliefs about theta before seeing x, before seeing our data, x. So before we looked at our data, what were our beliefs about r, or beliefs about theta? What did we believe about coins? We probably felt that coins land heads 50% of the time. Maybe we could be mistaken or something. Okay? I don't know how to draw arrows, but I will do this. Okay, and here I've got the probability of x given theta. This is our likelihood. This is the probability of our data given a certain parameter value theta. Okay, is that, and so this is just our probability density, okay, multiplied out for all of the different values we observe in our x. Okay, so this is just kind of the I'll say okay, yeah. The product of each value's, I guess, probability density. And then, okay, and then lastly, we have this probability of x. This is what we call our marginal distribution. It's just a name. It's what is the probability of getting the exact data that we observed in all possible circumstances. Okay? What is the probability of getting the exact data we observed for, all kind of possible scenarios. So that would be things like, what's the probability of getting the exact data we observe for all possible scenarios? This does not depend on theta, okay? So probability of x does not depend on theta. It's a function of x, not a function of theta. And so when we are bringing it into this thing, which is the probability of theta given x, this is a function of theta. So this thing behaves as a constant with respect to, as part of this function, okay? So this does not depend on theta. And in fact, it is a constant. It's just a constant, okay? And this thing, this marginal distribution, it is often can be very complicated to calculate, right? So you've got your data, and then somebody says, what's the probability of getting this exact data under all possible scenarios that exist in the world? That's like a difficult question to answer. But the nice thing is that it's just a constant, okay? And so a lot of times we just ignore it. We just say, oh, it's a constant. I'm going to just change this thing from equal to proportional to, okay? So, so it's just a constant, and so because it's a constant, I'm going to flip to the next slide here. So we've got probability of theta given x is equal to the probability of x given theta times the probability of theta divided by the probability of x. Well, probability of x is a constant. So all we do is we just say this, I don't know how to write this symbol, is proportional to. And we just do this part, probability of x given theta times the probability of theta. Okay, so we just get rid of this. And we can kind of reverse solve for this because in order for it to be a probability distribution, this thing has to integrate to 1. So probability of x is a constant, and it's just a it's called a normalizing constant. It just makes sure that the probability distribution, when we integrate the whole thing, integrates to equal 1 so that it respects the rules of what a probability distribution is. Okay? It is proportional to, is just, so p of x is just a constant with respect to theta, right? And its value is whatever it needs to be so that the integral of probability theta given x over all possible values of theta is equal to 1. Okay, so this is the Bayes rule of Bayesian statistics. Okay, and so we will have to express what we believe about R using a probability distribution and what we believe, and we will update our beliefs about R using our data, and we will get a resulting probability distribution. Okay? And so this prior belief about theta, this could be any probability distribution you want it to be. Okay? It can be a discrete distribution, it can be a continuous distribution. It just needs to be a probability distribution and on theta. Okay? And so here we'll try we'll have a discrete prior. Okay. All right, so I think the example I don't know if you remember the example was we were looking at a carnival game and we were flipping coins or something, right? And we said, is the carnival or the casino or whatever I said, are they using a fair coin? Okay, let's say we live in a world where there are only 2 types of coins, okay? So let's say there are 2 types of coins. Okay, type 1 is a fair coin, and type 2, so fair coin has R is equal to 0.5, and type 2 is an unfair coin, and the unfair coin has R equal to, I don't know, 0.8. Okay, I'm just making this up. So these are the only 2 types of coins that exist in the world. So whenever you flip a coin, you might be dealing with one, you might be dealing with the other. Okay. All right. So we can let's express our beliefs, our prior beliefs about theta, okay? Or I guess about R. Okay, and so R can have 2 values. It could be 0.5 or it could be 0.8. And we can say, before you viewed the game, what do you think? I don't know, let's say fair coins are much more common, so you say, yeah, you know what, I'm going to give it a 90% chance that it's a fair coin and a 10% chance that it's an unfair coin. Okay, so this is like, before you even view anybody playing the game, you're like, I'm going to guess it's fair, or something like that, right? So this means I believe we have a fair coin with 90% probability. Okay, does that kind of make sense? All right. So we come in believing the coin is most likely fair, but we'll have a 10% chance that it's unfair, right? Okay, and then we observe our data. What was our data? We said 10 flips, and we got 9 heads and 1 tail. Okay, so now what we have to do is we have to say, all right, what is the probability? So this is the probability of R, and we're going to say, what's the probability of X given R? Okay, because what we're going for is the probability of R given X is equal to the probability of X given R times the probability of R divided by the probability of X. Okay, so this is going to go a couple ways here. Okay, so first we'll do 10 choose 9. So we'll do, first one will be for R equal to 0.5. So this will be 0.5 to the 9 times 0.5 to the 1. Okay, so this becomes, shoot, I did not bring my calculator. All right, can somebody do this math for me? No, I'll do it. This is just d binom. Oh gosh, I haven't posted the homework. I know, I'm the worst. Okay, all right. So d binom 9, 10.5. Okay, so this ends up being 0.00977. 00977. Okay. All right, and then the other we have for R equal to 0.8. We have 10 choose 9, 0.8 to the 9, and 0.2 to the 1. Okay, so this is d binom 0.8. Okay, and this we have 0.268. 0.26844. Okay, and then okay, so let's take a look at this. So that we have the probability of X given R equal to 0.5 was 0.00977, and then the probability of X given R equals 0.8. This is 0.26844. Okay, and then over here, before we had the probability that R is equal to 0.5, this was 0.9, and the probability that R was equal to 0.8, this was 0.1. Okay, so I'm going to multiply these two. And so here I've got the probability that R is equal to 0.5 times the probability that X of this, given that 0. Is equal to, I don't know, what is that? D binom times 0.9, 0.00879. And then over here, well, this is easy. It's going to be 0.026844. Is this okay? All right, and so this is technically the probability of X and R equal to 0.5, and this is the probability of X and R equal to 0.8. So the probability of x is going to be equal to the probability of x and r equal to 0.5 plus the probability of x and r equal to 0.8, right? Because this covers all possible scenarios. We live in a world where there's only two types of coins, so either we have the fair coin or we have the magic 0.8 unfair coin. Those are the only two possible scenarios. Because in our world, it is literally impossible to have a r equal to 0.49 or anything else, okay? So there's only two ways of getting this exact data of 10 flips and 9 heads, and it was either this way and the probability of getting that is this, or it happened this way and the probability of getting, well, the unfair coin was this, okay? And so the total probability of my data, this is our marginal, is going to be, this math is too hard, 0.1 times d binom 910.8. Okay, so this adds up to 0.03563. 0.0356. What? I think 3. Okay, this is funny to me. All right. Okay, and so now we get our posterior distribution. The posterior, so we have our marginal, and then this is our likelihood, and this is our prior. All right, and this is our marginal. Okay, so the posterior, which is probability of theta given x, this is going to be, we get a distribution. So we have the probability, or in this case, sorry, r. The probability that r is equal to 0.5, this is going to be 0.00879 divided by 0.03563. I should save these values. Okay. So this is going to be called the margin. Hard time here. So this is my margin, and okay. So R.5 is what was that? That was d binom 910.5 times the prior of 0.9. Okay, so R5 is that. R5 divided by the margin is 0.2467. And then the other probability that R is equal to 0.8 is 0.026844 divided by our margin, I'll just write marginal. And this is, well, basically going to be 1 minus that, right? So 0.7533. And this is our updated beliefs now, okay? So we came in believing that the coin was fair, 90%, with the probability 90%. After we see this game where the person flipped 9 heads out of 10, we go, oh, you know what? Now I am more inclined, 75% that the coin is unfair, and only 25% that the coin is fair. Okay. If we started off with different beliefs, that, yes, question.
So on the left-hand side, is it given the data? Like, given x?
Yeah, so given x being 9 heads out of 10 flips.
So it's like, it carries over to the next, like, to the right-hand side? We have just P of R equals 0.5.
Yeah. P of R is 0.5. I'm sorry, yeah, given the data. Sorry, I'm sloppy in my notation. So yeah, this is what we call our posterior, and so we've updated our beliefs after seeing the data, okay? So we came in, before looking at the data, inclined to believe that it was a fair coin, because of course people are gonna play fair, right? And then we come in, we look at the thing and we go, this is a little bit hard to believe if it was fair, and so now I'm more inclined to believe that it's unfair, okay? If you came in with the preconceived notion that the world is full of scammers, then this would just further solidify that belief, right? So here, if I came in, so let's say, so the math, here, I'm just gonna copy this entire thing, and I'm just gonna make a new slide with all of this stuff, okay? And then now, what we're gonna do is we're gonna come in with different prior beliefs, okay? Different prior beliefs. Okay, we think, you know what? Those carnival people, those are shady people. I'm gonna think, I would be surprised if they were playing fair, right? So we give them, they're playing fair with 10% and they're playing unfair with 90%, okay? So we do something like that, and so our numbers here would change. So if we came in with kind of these beliefs, then the data we observe would change, right? My likelihood remains the same because it's just saying if the coin was fair, what's the probability of getting 9 heads out of 10? If the coin was unfair, what's the probability of getting 9 heads out of 10? Okay? But now we're gonna say, I'm coming in, I'm thinking, you know what, I don't trust you to begin with. You are a carnival person, the worst kind of person. And so we're, I'm sorry, no offense to carnival people. And so, you know, we come in and then we get, all right, so this is gonna be 0.000977. And this is, I don't know what this is. This is D binom 9.8 times 0.9, 0.24159. 2419. I can't. 159. Okay, and then and so when we combine these, this plus okay, I get 0.242. I should save this as the marginal. .24257. Okay, and so I have 0.000977 and 0.24159. Okay, and so so 0.1 times that divided by the margin. Okay, and so this becomes 0.004, and then this will necessarily be 0.996, right? Okay, yeah. And so prior to seeing the data, I had this notion that they were more likely to play with the unfair coin than the fair coin. And then after seeing the data, that just confirms my suspicions to begin with. And so now I have I'm quite convinced, 99.6% sure that they're playing unfairly. and it would take a remarkable amount of other data to convince me otherwise. So now the next game I see, I'm going to have these as kind of my beliefs now. Okay, so we are taking our prior beliefs, we look at the data, and we update our beliefs accordingly. So depending on what you believed prior will determine the beliefs that you have after seeing the data. Okay. All right, does this kind of make sense, what's happening here? Okay. Oh my gosh, okay. So this was a simple example where we said in our world, there's only two types of coins, the fair coins and the unfair 0.8 coins, okay, because somehow those exist. More likely though, it probably makes sense to express the distribution about how often a coin lands heads with what we call a beta distribution, a continuous distribution between 0 and 1, okay? So it probably makes more sense to express our beliefs about a coin's probability. Oh, let me close that online poll. How do I? Shoot, I don't know how to do this. Dashboard, manage, close poll. Okay. Okay, about a coin's probability with a continuous distribution between 0 and 1. Okay. So when you guys learned about the beta distribution, right? In like 100A, 100B or something. What did they teach you about the beta distribution? What can you tell me? Okay. Well, it's a continuous distribution that goes between 0 and 1. Okay, we can tell you that. There's two parameters, an alpha and a beta, or what is it? I don't know. So you got like the beta distribution, and there's two shape parameters here. Let's go to Wikipedia and see what they call it. All right. And the beta distribution, the PDF for the beta distribution looks like really scary because it's got like these gamma functions, and it's like, what's a gamma function? Okay, so the beta distribution, you know, it can take on all of these crazy shapes between 0 and 1, and then the PDF has, you know, x to the alpha minus 1, 1 minus x to the beta minus 1 divided by beta alpha beta, where beta alpha beta is gamma alpha gamma beta gamma alpha plus beta, and you're like, oh, okay, well, of course. All right, so this is, what is it? It's x to the alpha minus 1 times 1 minus x to the beta minus 1 divided by beta alpha beta. Okay, all right. All that matters is the numerator, okay? This is just a normalizing constant, just a constant. Okay? And the constant is like, so forget about it, okay? It's just a constant. This part, the numerator, does the numerator look like anything? It looks kind of like binomial, right? Because if you think about binomial, so recall binomial, you have, it's going to be something like theta to the, what is it, theta to the k times 1 minus theta to the n minus k, or something like that. So this part looks kind of like that, except it's not k, it's alpha and beta. But anyway, it's a continuous distribution between 0 and 1, and if you have something like beta 1, 1, you get this, you get a flat distribution, and then if you have beta like 5, 5, you'll get this distribution, and if you have beta like 500 comma 500, you'll get, so everything goes from 0 to 1, all of these things. Beta 500 comma 500 looks like this. You know, beta 5 comma 1 will look like this, stuff like that, okay? And it's just like, or if you do like beta, you get like weird things like 1.5 times 1.5, you'll get like, just all these funny shapes. Okay. The reason why we use the beta is that there's this, because the beta and the binomial have these similar forms mathematically, it's known as the conjugate prior for the binomial, okay? The beta distribution is the conjugate prior to the binomial distribution. Okay? So, conjugate prior, this just means has nice math properties, okay? It sounds like it's all fancy. It just means it makes our math convenient, okay? So that's what it just means. The beta distribution makes our math convenient when we're dealing with a binomial situation, which is what we're dealing with because we're flipping coins. We're flipping coins, we've got a binomial situation. The beta distribution is a probability distribution that has nice properties for that, okay? One way to think about the beta distribution and the shape parameters alpha and beta. Beta has alpha and beta shape parameters. And they can kind of be like, what are your beliefs about, what are your beliefs about a coin if you have seen it land heads alpha times and seen it land tails beta times? Okay, sort of. Okay, but this is kind of a helpful way to think about what it means. So when we had, here, I'm going to just kind of throw some plots up here, and I apologize for going a little bit over here. So let me just do x is a sequence from 0 to 1, by is equal to 0.001, and let me just do d beta. So we're going to plot x against d beta with shape parameters 5 comma 5 type equals L. Okay, so if you've never seen a coin before in your life, right, and you see it land heads 5 times and you see it land tails 5 times, you're going to be inclined to believe that it's going to land heads with a probability of 0.5. But you're also open to the possibility that it could land other things because you've only seen 5 flips, right? On the other hand, if you've seen the coin land heads 500 times and tails 500 times, you are very inclined to believe that the coin lands heads with probability 0.5, okay? If you've seen the coin land heads, let's say 8 times and tails 4 times, okay? You're going to be inclined to believe that it's more likely to land heads than it is tails. And likewise, if you've seen it land heads 80 times and tails 40 times, your certainty about its probability landing heads more often than tails is going to be, you know, even more precise here, okay? And And lastly, you know, if you've seen it land heads like 10 times and tails like once or 0 times, you know, you're very inclined to believe that it has a very likely heads property, or likewise the other way is 1 comma 5 or something, it'll go that way. If you've seen it land heads basically once and once, then, or just knowing that those two sides exist, it's kind of flat everywhere, and likewise. So if you saw it land heads twice and tails twice, you get something that looks like this, and there's all sorts of like weird things that you can do in between, okay? So that's kind of what the shaped parameter, alpha and beta, means for this. I guess we've run out of time, so we'll have to continue talking about the beta and the binomial and how they work together. I know I said I'm going to post a homework and I didn't get around to it. I promise I will post the homework and I will give you time to finish it. So that will be coming this weekend. Okay, have a great weekend. We'll see you guys on Monday for week 6.